Well, thank you very much. It's a pleasure to be here and to, virtually that is, and to be seeing all of you. And I also want to wish you all Chodesh Tov uh, and a very successful school year. So I'm going to turn this on now. Oopsie. I have to try to get to the beginning now. Yeah. So the talk is about a general algebraic structure theory, which was inspired by tropical mathematics, and that's its
תודה
main
רבה.
application. Um, but so let me just say a few words about tropical geometry, tropical mathematics. It was invented by Imre Simon. That's why it's called tropical, because he was living in Brazil and the French wanted to honor him. And an attempt to take usual mathematics and maybe simplify it by taking logarithms. You would take some sort of curve, and you would take the logarithm and as t goes to infinity, it would sort of shrink to a kind of stick structure. I don't know. I used to make a joke about um, the judge in this movie. Anyway, it looks like a stick structure, and you can analyze that, and then you can use that to keep certain invariants and therefore study the invariance. Intersection theorems have been very successful in this sense. And so I just want to notice that when you take the logarithm, multiplication, of course, turns to addition. Addition sort of turns to maximum. If you have the sum of two highly unequal quantities, then it approaches the maximum. Of course, if these are the same, then this fails. You get log of 2. But anyway, so traditionally, the max plus algebra, where addition, the old addition becomes, the old multiplication becomes plus, and the old maximum becomes the new plus. That is a semi-ring. And in other words, it has all the properties of a regular ring, except it doesn't have negation, because you can never go back to minus infinity. So anyway, another more modern application maybe is if you look at the coronavirus, two people might infect each other according to the maximum of their infection. And so it might have some bearing, although I don't think anybody's done this in a very systematic way. Well, actually, I have some colleagues in France who are analyzing the corona from that point of view. So anyway, so you have the semi-ring, and but it doesn't. There are two problems with the semi-ring. One is, as I mentioned before, it's not really max plus. When you take the logarithms, it's almost max plus. And also, you have a problem when you take what's the interpretation of the maximum of an element in itself. I'll get to that in a minute. Anyway, more recently, people have viewed this through evaluation theory. And there's this idea that you use the Puiseux series, which are all power series, with except that the powers are rational numbers rather than integers. And they have to have a common denominator, or else the addition is not, no, the addition is, the multiplication is not well defined. And so if you have that, you define the valuation. This should be a j, the minimum of minus j over n. And so let's see if I can move this over here. The target is was viewed as the max plus algebra, but this is not really true, because if you have two series with the same leading terms, then they can cancel, and then you have the value of the sum of the series greater than the original series, than these two twos. So this is what I was saying before. If you're going to use the Puiseux valuation, you don't quite get the max plus algebra. So you have a plus b as the maximum of a and b, except when a equals b. So this is what I have on this slide. So we'll bear this in mind. This is actually a major point that we want to use. Okay, so we're going to define, so this problem about what a plus a should be, we don't really know what a plus a is. It's could be anything greater than a or equal to a. So Tsuryasakian actually addressed this matter with in his thesis, which he lectured here maybe, I think close to 15 years ago already. And so what he did is he took two copies of the object that under study. So you have this tangible copy and the ghost copy, T and G. And normally T is isomorphic to G, but it doesn't have to be. And then the sum of two elements with the same value will move from the tangible to the ghost. Okay, so that's the idea. You have sum of two tangible elements is the maximum when they're separate, and a plus a is the ghost of a. Okay, so this is the supertropical semiring. So let me say it a different way. You have the tangible part is what you want to study, but in order to get a good algebraic structure, you have to introduce this extra layer, the ghost layer. So, so here, ghost elements, and we have the tangible elements. And they don't have to be a monoid, but they usually are. I have implicitly assumed that there's some sort of order involved, because I was saying you take the maximum. That also can be left aside, and we'll discuss that more generally. But we have this idea of the supertropical domain with these two layers. Okay, and this is the addition, which I was saying before, in the supertropical algebra. Okay? Please try to remember this. This is very important. That you take the maximum or you move up one layer. Okay. So I mentioned Zur Yitzhakian before, and later on we joined in with Knebusch, and we studied this in quite many different perspectives. And what happened, well, especially in the initial work with Zur, there were some theorems that came about paralleling the classical theorems, but not quite the same in linear algebra. One had to make certain modifications, but there was some sort of mysterious connection that if you made these modifications, you could transfer classical theorems, classical algebraic theorems to theorems for this. And so this bothered me for some time. I was trying to wonder if it's just some amazing coincidence that you get these theorems, or whether there was some underlying structure, because one would hope that that was the case. By the way, I can't seem to see the time. So if it gets to be like a quarter till or something like that, please let me know. We tried, so various other people have been involved in this. Here's a list of the people. And let me continue with this. So what are we interested in? We're interested in a set that doesn't have enough structure. And that's called T. And we're going to embed it in a larger set, A, which is easier to study algebraically. So here are some examples which I'm not going to study. If you have an integral domain, the non-zero elements is a monoid. But we can study it better by studying all the integral domain. Graded algebras, you often want to study the homogeneous elements, but you have to go to the graded structure in order to understand what they are. In the vector spaces with a multiplicative base, such as group algebras, you want to study the group by looking at the structure of the group algebra. Or in half algebras, it's the same sort of thing. You might be looking at the group-like elements. For functions, you might want to study the characters of a group, and you study the characters of the group by going to the algebra of class functions and studying them there. And also with a hyperfield, whatever that is, you often study a hyperfield by its power set. We'll get to that, hopefully. So, so these are the kinds of questions one wants to ask. We want to, oh, I lost the top line here. We want to look at this A and try to define geometry, dimensions, linear algebra, invariance. And we want to study all the classical algebraic geometric ideas with one hand tied behind our back. What's tied behind our back? We don't have minus. We can't get to zero. And all of this stuff is, always defined in terms of groups. And so here we have to use semigroups. So it doesn't have to be associative. So you just start with a set with some sort of multiplication. And then you define a module in the usual way. Module doesn't really need negative in its definition. So you can define a module over any multiplicative set. It has to be an additive semigroup acting on the set. And so we call T the tangible elements. And so here's maybe the principal idea of this whole talk is that since you don't have negatives, you have to make something up that's going to act like minus, because you really need minus in order to do anything. So a negative here, a negation map, will be something like negation, satisfying all the properties of negation, except that A minus A is not zero, not necessarily zero. Because in the max plus, you can't get to zero. It doesn't have any negation. So what's the usual property of a negation? That it associates with the multiplication. And if you have addition, it will also distribute over addition. And so we're going to write it with a parenthesis to distinguish it from the usual kind of negation. Well, first of all, and so you have, you won't get zero all the time, so we'll call these quasi-zeros. All A minus A's will be called a quasi-zero. And this will be an ideal, or this will be a distinguished subset of A. If A is a semi-ring, this will be an ideal. Now, this mysterious connection that I was saying before is that in normal algebraic theorems, if you translate the zero to quasi-zero, you often get theorems. Not always, not 100%, but 80% of the time you get theorems. Okay, in order for the theorems to be provable, you need some more properties of the negation. You need this property that if A minus B for two tangible elements is a quasi-zero, then B equals A. Of course, this is true in the classical situation. If A minus B is zero, then B equals A. But this can be, not zero. It could be some quasi-zero. And so the max plus semi-ring fails that, but we're going more in direction of Itachian's supertropical ring rather than the max plus ring. Okay, now there are two possibilities. Negation, actually, the plus is negation if you think of it in a kind of weird way. If you erase all the minus signs here, I mean, plus obviously satisfies this property. So the identity map is a perfectly good negation. And in fact, that's what's used in supertropical mathematics. But then there's something called symmetrization, which is parallel to the classical way that you define negation. When you define the integers from the natural numbers, you take pairs of natural numbers and you say this is plus and this is minus, and then you consider the equivalence classes. So, so the way that the integers are defined from the natural numbers, you can do this for any semigroup. And so this is this is a very useful kind of negation. We call this the second kind because minus A is not equal to A. First kind minus A equals A, second kind minus A is not equal to A. And so our main structure here will be a triple, or we'll start with a pseudo triple. A is a module over T, and it's equipped with negation. We also want another property that none of the tangible elements are quasi-zeros. That's perfectly reasonable, right? Zero, if you start with the non-zero elements of an integral domain or something like that, zero is not among them. So here, the quasi-zeros will not be among the tangible elements. And well, you can introduce a kind of sign here if you have the positive elements and the negative elements. I'm going to skip that. Well, like when you form the integers from the natural numbers, you sort of declare that the natural numbers are positive, and then the negative part is the negative. Okay. Now, remember we were saying at the very outset that A plus B should be the maximum of A and B. So even if you don't have an order, you might have that property that A plus B is one of the two. And so that's an important property also. We call that minus bipotent. And it distinguishes between when B equals A and B is not A. When B is equal to A, you get A circle, the quasi-zero. Okay. You can generalize that a bit and still come up with a theory, a reasonable theory, just saying that the sum of two tangible elements must be tangible unless one is the negative of the other. So you have, of course, 1 minus 1 will be an important element. That will be one circle, the quasi-zero of 1. And if you add 1 again, you get, we'll call that E prime. Oh, ironically, in the supertropical case, once you get to a ghost, you can't leave, it stays a ghost. So in the supertropical situation, E prime equals E, although that might seem counterintuitive. In the classical situation, of course, E prime is not equal to E, because E prime will be 0, E is 1, E will be 0, and E prime will be 1 again. It'll be 1 minus 1 plus 1. Okay. So we'll call this tropical type if A is either T or the quasi-zeros. That's what we had at the very beginning. And we'll call this new thing hypergroup. Hypergroups have come up recently. And so I wanted to relate them in this theory also. A hypergroup, well, I'll just mention it quickly. A hypergroup, the sum of two elements need not be an element, it's a set. Okay, so everything's viewed inside the sets. I'll get back to it. What time is it now?
It's 25 past. You spoke about 25 minutes.
Okay, great. That's good. So yeah, so in another 20 minutes, let me know, please. So we're going to get to hypergroups later, but in principle, you start, T will be this hypergroup, and then A will be the sums of elements of the hypergroup, and so it will be in the power set of T. And you take addition element-wise. That's what this means. Let's see, where was I before? Okay, well, okay, so we have these quasi-zeros, and in order to get an analog to classical theorems, you need something to replace equality. Equality won't work because well, like you can't get to 0. And so you want to identify all the quasi-zeros, and they're not equal. Okay, that's a good way of saying it. So equality can't possibly work in this theory. in any reasonable way. So we replace equality by something which we call a surpassing relation, which has all the properties of equality except symmetry. It's usually anti-symmetric. And it could be like an order, though it doesn't have to be. It just looks like an order, doesn't it? This condition is very important, though. A tangible element cannot surpass a quasi-zero. This might look counterintuitive, but let's think of it as follows. A plus A is a circle, usually, in most of the examples. And a circle will surpass A. A does not surpass a circle because a circle is A plus A. Okay, so that might justify that. Anyway, so that condition is needed. I'm not sure, did I mention that you also want the tangible elements to additively generate everything? You want everything to be a sum of tangible elements. Okay, so for example, A0 is A plus A. Okay. And these imply that if these two imply that if you add a quasi-zero, you get something that surpasses B. And in fact, this is the way to think of surpassing. Surpassing means that you get an element that surpasses the first element if you add a quasi-zero. Okay. And so that's, in fact, our main example of a surpassing relation. Just this. Okay. And you can check that it's a surpassing relation. You can go the other direction also and define the null. If you're given a null set, this would be like the set of quasi-zeros in one interpretation, then you can define a surpassing relation. So this is almost general. Okay. Okay. So so this is just propaganda that we need negation maps and surpassing relations to be able to formulate theorems. Okay, so of course, this all sounds like universal algebra in a sense. As soon as you start talking about semi-rings and things that aren't quite rings, you have the idea of universal algebra where you have operations and identities and unary operators are distinguished elements. And you can form a structure theory, but this surpassing relation messes things up a little bit because it's not an identity, because it's not symmetric. But nevertheless, we use universal algebra as our inspiration in this. Okay, so a system will be a T module, a negation map, and a surpassing relation. Okay, and we're going to say that if the sum of two elements is a quasi-zero, then these are negatives. But okay, the way I said it, it sounds like unique negation, but this is slightly more general the way it's written. Okay, so in classical algebra, the quasi-negative is the usual negation, and the only quasi-zeros is zero. And so surpassing is just equality. So this theory does generalize classical mathematics and is parallel to classical mathematics. Often T will be a monoid, it doesn't have to be, but oh, I should have mentioned that Dress actually defines something like supertropical algebra 20 years before Itzakian's thesis, but it was in a different context, and I don't think he was thinking in the same way. So we have this supertropical system, which I pointed out before, which here, the quasi-zeros are just the A plus A ghost. So two elements, one surpasses another if you add a ghost element to it. Okay. And here E prime equals A. Symmetrization is like this Bourbaki, excuse me, like this Bourbaki construction. So you have anybody who studied, you probably studied this in first year structure theory of algebra or something, but elementary structures. But this is the multiplication when you form the integers. And so if you start with tangible elements, the tangible elements will be those elements that are tangible in one component or the other, and zero in the other component. Well, so if the tangible elements span A, then these tangible elements span A hat. So we're in the right ballpark. The negation is, of course, the switch, because this is the positive part and this is the negative part. So A minus B goes to B minus A. The quasi-zeros are the AA. In fact, we're just following Bourbaki's construction, everything except that you don't go modulo the equivalence at the end. You see, what you would do then is you'd say this is equivalent to 0. You don't do that because otherwise everything would degenerate. So you do the whole theory except with that equivalence. That's the symmetrized system. Okay. All right, so going from A to A hat takes you from an arbitrary T module to one with negation. So that's a useful functor. Okay, so I was talking about the integers. This isn't really the integers though, because you're not modding out n. So this is what I wrote here, that mn is not the same as n plus k, n plus k. They're both quasi-zeros. Okay, semigroup, hypergroup. Hypergroup has this binary operation addition, hyperaddition to the power series. Okay, and then you require associativity, although that's sort of tricky to state because you're already getting to power sets. Okay, that's what I was saying here. Once you do addition, then you have to go to the power set, which, as I said, you do power set addition just element-wise, so that's not a problem. Then you have a hypernegative. Hypernegative in the literature is that A plus A, this set, contains 0. And that's a special case of what I was saying before, that you could, well, here, let me just continue. So you have hypernegation, and hyper 0 is the set A plus A. And it's called a hyperfield if the tangible elements is a multiplicative group. Okay. So I wanted the structure to be additively spanned by T. So I'm going to replace the power set by the subset of sets which are spanned additively by the singletons. T is identified with the singletons. So our surpassing map now is simply set inclusion. Okay, so something is greater than 0, surpasses 0, if and only if 0 is an element of the set. And that's why we had 0 being an element of the set here. Okay, so this is another example of system, this thing here. And it's pretty natural. After all, this is a natural relation. And so this is one example. If you look at this example, you get something which is isomorphic to the supertropical mathematics, supertropical summary field. So supertropical summary field can be viewed in terms of hypersystems. Okay, and this was actually observed by it was after Zur invented his tropical mathematics. Okay, this is another example of a hypersystem, the Boolean hypersystem, where you have 3 elements, the Boolean algebra and the quasi-zero formed by 1 plus 1. Okay, so that's the Boolean hypersystem. You can view it this way, that 1 plus 1 is 0, 1, minus 1. So this is like one ghost, this set. Okay, anyway, so this is a system. Oh, there are other systems. There's a system of signs. I think of, this is a nice system. I mean, this is a nice hyper field. You take the circle and you have the hypernegative of A is the antipode of A. But otherwise, the sum of 2 distinct points is the arc joining them. And this system fails. The sum of 2 tangible elements is not tangible here. It's an arc. It's not the tangible elements of the points are the and so the sum of 2 tangible elements is not tangible. But it does have unique negation. And here's one that's even worse. It's a very beautiful hyperfield where the sum of 2 elements is 2 points, each are considered as points, is the point that creates a Euclidean triangle. Well, there are a lot of those. There are a lot of ways of making right-angled triangles. And I'm sorry, not right-angled, just Euclidean triangles. There are a lot of ways of making Euclidean triangles, so this will be a set. And this hyperfield is not distributive. Multiplication is not distributive over addition. Okay, so anyway, that's some taste of hypersystem. Then there are fuzzy rings. Fuzzy, I told you that Dress anticipated Itzakian. He did this with fuzzy rings. And this isn't exactly the definition of a fuzzy ring. It's one of the axioms of a fuzzy ring, though. And so if we take this axiom on a system, we call this the fuzzy property. And every fuzzy ring is a system. So fuzzy rings turn out to be examples of systems. So you see that the systems encompass quite a few things. They also generalize tracks by Baker and Bala. Okay, so we have systems, but if we want to do something with them, we need to have secondary structures. The way that if you want to do something with rings, you need to take polynomials and matrices. So polynomial system is completely obvious. You just take the polynomials and add them component-wise, multiply them like polynomials, and the negation will be wise. The tangible elements, okay, so that's multiplicative. So polynomials. See, once you have a system, then you can take say that this has a root, or there's a root of the polynomial when it's a quasi-zero, not a zero. And this turns out to be exactly the same as corner roots in the language of tropical mathematics, but it's more algebraic. Corner roots are combinatoric, but they're very hard to study algebraically. This is very natural in the structure of this system because it uses the analog of equality. Okay, and you can get into Stellentis. One of the first things that Sura and I did was this in tropical mathematics. I'm not sure anybody ever did it in terms of a system. Okay, anyway, you can form matrices. Again, component-wise addition. The tangible elements will be the matrix units multiplied by a coefficient. Won't get a monoid anymore, but if you adjoin zero, you get a monoid. Okay, and let's see if, so what is the systemic version of determinant in this matrix theory? Well, you do the same thing as you always do, but minus doesn't exist, but you have this negation function. So you apply that and you define the determinant. And then the very, very pretty fact is this. You can hardly see it. The determinant of A times the determinant of B will not be the determinant of AB because you have too many terms. AB has extra terms when you compute the determinant. But the extra terms all are quasi-negatives of each other. They come in pairs, which produce quasi-zeros. So therefore, AB surpasses the determinant of A times the determinant of B. And so this, you can do this, the generalized Laplace identity also.
Ask me to warn you when it's quarter to.
Great. Okay, thanks. So warn me at 5 till now, please. So you have this, and here you actually get equality. This is there's the generalized Laplacian identity for determinants, in using determinants of minors, and this holds using this negation functor, negation map. It's quite funny that that works. Now you can define the symmetrized determinants in the symmetrized algebra, and you can interpret that this equality in the symmetrized algebra. Okay, next. A non-singular matrix, of course, will be one where the determinant is tangible rather than non-zero, right? Now, actually, there are four possible definitions of singular, depending on how bad you want it to get. Either it's the quasi-zero of a tangible element, or any old quasi-zero, or it suppresses zero, or not tangible. These are often the same thing. When the system is tropical type, these are all the same. Okay. You can have the submatrix rank, the largest non-singular submatrix. You can have dependence. Of course, that means that the sum of a linear combination surpasses zero, not equals zero. And then amazingly, you often get that these are all the same. In the standard supertropical system, the row rank, the column rank, and the submatrix rank from the last slide are the same. But it does not work for the signed hyperfield system, and also fails in the symmetric symmetrization. Let's see if I think I have an example there. Then you can talk about span vectors. V is spanned by the others. This is not the same as dependent. So I call them surpassed independent. It's not the same as the previous thing, because this surpasses this implies that this minus this surpasses zero. But if this minus this surpasses zero, it doesn't mean that this surpasses this. Okay. This is a matrix I wanted to show. This has row rank 3. The rows are independent, but every square submatrix is singular, amazingly enough. So it has row. What is this? I think this line shouldn't be there. Okay. What about a tensor product? Well, you can define a tensor product for modules over semirings. You don't need a negative to define tensor product. That's been well known for years. Many people have studied tensor products over semirings. Then you can define the tensor semi-algebra. Use the free module usual way. And then what about the negation? Well, you don't have a negation. But if you have a product of at least two vectors, you can always define EI, EJ to be minus EJ, EI. So ironically, you get a negation map in the tensor semi-algebra for all vectors, for all tensors of length at least 2. So if you consider this sub-algebra of the tensor algebra, you get a system. And you can get an exterior algebra, usual way. So here, V times V is not, I mean, V1, yeah, V1, V2 plus V2, V1 is not zero. It surpasses zero. It's a quasi-zero. Okay. And then you can extend by induction and get this. So this is what I said before. You have this triple, and you can just define the surpassing relation in terms of adding a ghost, adding a quasi-zero. These are the quasi-zeros, the span by the V tensor V. Okay. And this has been used to prove classical analogs of classical theorems in the tensor, in the Grassmann algebra, which generalize the Cayley-Hamilton theorem. You can get the Cayley-Hamilton theorem from this. Okay. Well, so what are the matter-tangible theorems systems? I gave some examples. And so a natural question would be, how can we classify them? And let's see. So if the negation is the first kind, then you have either a bipotent system, minus bipotent system. So they're very close to metatangible. They're a special case of metatangible. Or you could have 3 equals 1. If 3 equals 1, that means 1 plus, it's not 1 plus 1 equals 0, because 1 plus 1 is a quasi-zero. But if 3 equals 1, we call that characteristic 2. And the classical algebra is example, but there are many interesting examples of this. Or minus could be the second kind. Again, the leading example would be bipotent. And in this case, minus bipotent will be really idempotent because A is not A. So A plus A has to be in the set AA. So it has to be A. Or again, it could be not minus bipotent, and then again, 3 equals 1. And this is a very strange situation, but it exists. Okay. And so to classify these, you need lots of examples. I actually don't have a full classification, but close to
Sorry,
5 more minutes?
Yeah, 5 minutes.
Okay, great. We're going fine. So there are all sorts of interesting examples that don't really come up in tropical mathematics, but they arise in this context. I think there's a very interesting kind of semi-ring. I'm sure it's, yes, Stu, I'm sure he knows the whole theory of this. But where you can't pass a certain number. In other words, once you get up to a certain number, then the sum remains that number. So we call that truncated, sort of like it's a glass ceiling. And oh God, in the last few minutes. Well, once you have this theory, you want to have this module theory also, right? Obviously. So in order to define a module, you define morphisms. And morphisms are defined instead of equality in terms of surpassing. So everything you would think of writing for a module, you write with the surpassing relation. And well, you know what? Okay, so you could, a fuzzy homomorphism is a morphism in that sense, if you happen to deal with fuzzy rings. But let me just say that the tropicalization with at the very beginning is a morphism. It's not a homomorphism. Valuation is not a homomorphism, obviously, but it the valuation is a homomorphism from multiplication to addition, and the extra valuation property um, um, satisfies this surpassing thing for morphisms. So you get a yeah. So you get a representation theory using this notion of morphisms, and actually June and Mensheva and I have been working on this, and it turns out Kahns and Kanstani didn't do systems, but what they parallel systems, and so we can sort of mimic many things of what they did through the systems and express it in a slightly different way. Okay, so thank you very much.
Okay, let's thank the speaker. Okay, so we have maybe a couple minutes for questions. Are there any questions?
Oops. Hello, do you hear me?
Yeah, sure.
Can I ask so I have two questions. So one is general, one is like comment, I don't know. So maybe I start with comment more specific for regarding representation theory. So I heard few talks in this Zoom period about set valued Young tableau. So it seems natural, like coherent with this. They did it like in Lustig algebra, quantum algebras and so on, but maybe also in this setting, they play a role. So this is just.
Yes, actually, I just don't have time, you know, and energy to enter everything. But one thing that um, I thought should be examined actually young tableaus, and I'm sure that you know there's a representation theory from the young type representation theory for systems. I mean, it has to be, and anybody who's interested in looking at that is welcome. You know, I think you're absolutely right, and it probably would work out, and probably hyper tableaus would probably fit into that setting.
The other question is more general. So can you solve like classical problems not within tropical, this tropical setting with this theory? So is it useful for graded algebras that you mentioned or whatever?
Well, there's a paper by Blushield and Baker on proving Descartes' rule of signs using hypergroups, and which is, you know, the same kind of philosophy. First of all, there are these, I mean, tropical mathematics became famous with the solution of intersection theorems, proof of intersection theorems. And so that's not exactly tropical. And there are many theorems and analysis that are non-tropical, but approved using tropical methods. Schusten in Tel Aviv has a seminar in analysis, which is about half tropical. Most of the theorems in the seminar are not tropical, but about half the proofs that come up are tropical. So yes, I mean it doesn't have a separate life that way. You know, it connects to a lot of more standard mathematics. If that was your general question.
Yes, thank you.
Okay. Sure. So I think we should thank Louis again because we have a department meeting. But thanks very much for interesting talk. Okay.
It's my pleasure. Oh, by the way, the person who did this first major thing was Milkalkin. I should mention his name.
Okay.
Okay.
Thank you.
Thanks.
By the way, unfortunately, Professor Schuss passed away a couple of years ago.